So in the intro to differentiability video, we saw that f of x equals the absolute value of x is not differentiable at x equals 0. So this is the point x equals 0, or really I should say this is the point 0, comma 0. But keep in mind, however, that the function does exist when x equals 0 and is equal to 0 at x equals 0. And also the limits coming in from the left and right are both equal to 0 approaching x equals 0. So the limit exists at x equals 0 and it's equal to the function value at x equals 0. So the function is continuous at 0, 0. But it's not differentiable there. Now here are the graphs of f of x equals ln of x. You can see it as a vertical asymptote at x equals 0. And its derivative f prime of x equals 1 over x, with vertical and horizontal asymptotes at x equals 0 and y equals 0 respectively. But is 1 over x, is f prime of x equals 1 over x really the derivative of f of x equals ln of x? Well, we know that the ln function is not defined for x equals 0, for either x equals 0 or for negative values of x. It's only defined for positive inputs of x. And we also know that the derivative of any function, including ln of x, is the function that generates the instantaneous slope of at any given x value of our original function, which is in this case ln of x. So we should be able to plug in a value of x into f prime of x, and the result spat out by f prime of x should be the instantaneous slope at the corresponding x value for f of x, the original function. But notice that f of x is defined, f of x equals ln of x is defined only for positive values of x. You only perform that natural log operation on positive inputs. However, 1 over x is defined for any real number aside from x equal to 0. So saying that the derivative of ln of x is 1 over x implies that you can find the instantaneous slope of the curve where the curve itself does not exist, because the implication that 1 over x is the derivative of ln of x implies that you can find the slope for these values of x, because notice 1 over x is defined here, but the curve itself is not defined here. So of course you cannot find the instantaneous slope of a curve where the curve itself does not exist. So theoretically you could plug in -1 for x and get f prime of x is -1. But when you look back at f of x, there is really no point. There's no point on ln of x with an x value of -1, so there's really no slope to be found. So if we want an expression for the derivative of ln of x, we have to specify that f prime of x is 1 over x for x greater than 0. And accordingly, we must change the graph. So I have to erase this piece of the graph. What we have left is the derivative of ln of x. So having redefined this function, the domain of this derivative is identical to that of the original function. That is, you can find the instantaneous rate of change of ln of x wherever it is defined. And that's the same thing as saying that you can find the instantaneous slope of the curve ln of x wherever it's defined. Now this is in contrast to the absolute value of x, which had a point at which it was defined that did not have an instantaneous slope or an instantaneous rate of change. at the point 0, 0, the derivative is undefined. There is no rate of change at x equals 0, although there is a rate of change just to the left of it and just to the right of it. Just to the left of it, it's -1. Just to the right of it, it's +1. But the rate of change changes immediately. So right at x equals 0, there is no concrete rate of change for the absolute value of x. And certainly we could make a quick sketch of f prime of x in this case as well. Just be the piecewise defined function y equal to 1 for x greater than 0 and y equal to -1 for x less than 0. And with no value right at x equal to 0. So in this case, the domain of definition of the derivative is a bit less than the domain of definition of the original function. Now what if f of x is defined at all but one point? Is f of x differentiable at that point, i.e. the point at which it's not defined? Now here we're looking at an example of just that. We're looking at the function f of x equals the sine of x minus pi for x not equal to 3 pi over 2. So this is basically a graph of sine of x that has been shifted rightward pi units and also has a hole right where x equals 3 pi over 2. So it's not defined there. It has a removable discontinuity at this point. And remember, a removable discontinuity is one that can be removed or filled in. In this case, it's filling in a hole. It can be removed by redefining the function at that point. In this case, all we have to do to fill in the hole is to redefine f of x as some function g of x equals sine of x minus pi without this exclusionary clause at 3 pi over 2. And then this function is continuous for all values of x. So we have thus filled in the hole. But we're really interested in this original function here. Is the function, the one with the hole, is it differentiable at this removable discontinuity? Is it differentiable at x equals 3 pi over 2? Well, you might be thinking that it is differentiable at x equals 3 pi over 2 because as you're coming in from the right, the slope seems to be approaching 0 from negative values. And as you're coming in from the left, it looks like it's approaching 0 from positive values, so it's getting less and less positive. Coming in from the right, it's getting less and less negative. So it looks like the slope is approaching the same value as x approaches 3 pi over 2 from both sides, specifically the value of 0. But if you're thinking along those lines, your calculus teacher might freak out because a function is not differentiable where it's not defined. This function is not defined at x equals 3 pi over 2, so it cannot be differentiable there. To give you some intuition behind why, recall that f prime of x is the limit as h approaches 0, this difference quotient f of x plus h minus f of x over h. Remember, h is just x plus h minus x. Now, if we're interested in the derivative at a particular point a, we make the substitution x for x plus h and a for x. This becomes the limit as x approaches a of f of x minus f of a over x minus a. Now think about this for a second. This is the limit of a quotient, right? Now imagine if f of x if f at a does not exist. If f at a does not exist, so let's say this is, well, let's say I'll just label it dne. If f at a does not exist, right, then you're taking something and subtracting something that does not exist. You obviously cannot get a meaningful number in the numerator. So you have something that doesn't exist in the numerator, right? And if you can't really divide something that does not exist by something else. That just doesn't make any sense. So we've established that a function must be defined at a point in order to be differentiable there. But is that function being defined at that point the only prerequisite for differentiability at that point? What if a function is defined at a point but it's just not continuous there? What bearing does that have on its differentiability at that point? To help us answer that question, we have our friend here, the greatest integer function. G of x equals the floor of x, or int of x, greatest integer of x, whatever you want to call it. And this etc just means etc., so the function just continues in this pattern. Notice that there are finite jump discontinuities at every integer value of x. So the function is defined at these values, but the limits coming in from the left and right are different. For example, when you're coming in from the left, approaching x equals 2, the limit is 1, but coming in from the right, the limit is 2. So limits are not equal. So although the function is defined, the function fails to be continuous at these integral values of x. But really the question we want to consider is whether the function is differentiable at these integral values of x. Well, let's see. We're looking at, for example, x equals 2. When we're coming in from the left, it looks like we're dealing with the flat line y equals 1, right? We're coming in from the right, looks like we're dealing with the flat line y equals 2. So it looks like the slope's 1 coming in from both the left and the right. So you might be thinking that this function is actually differentiable at x equals 2, and similarly at all integer values for the same reason. But that's actually not the case. And why is that? Well, it turns out that continuity is a requirement for differentiability. A function cannot be differentiable where it is not continuous. So because this function is discontinuous at all integer values of x, it is also not differentiable at these very integer values, these very same integer values of x. In the next video, I'm going to run through a quick proof of the fact that continuity is a requirement for differentiability.